today's lesson, we're going to learn a few different ways to calculate concentration. The three types are going to be molar concentration, percent concentration, and very low concentration. Hopefully after today, you'll be able to recognize a few places where you see some of these concentrations being used in your daily lives as well. So what you'll want to have handy is a calculator and a periodic table, because today's lesson there's lots of calculating happening. So let's take a look at the first type of concentration. This one's molar concentration. So yes, moles are back in the picture here. When we look at molar concentration, the units that we have are moles per liter. If you want to use a formula based on those units, you can use the one that's shown here. C is equal to N over V. C is concentration, and it has to be in moles per liter. We know our little n is moles, so we still see our units of mole. And V is for volume, and we use liters when we do molar concentration. So let's jump in right away and try a problem with molar concentration. So here's our problem. Determine the concentration of a solution made by dissolving 29 grams of sodium chloride in 750 grams of water. So if we're trying to find concentration, that means we want moles per liter for our units. When we look at what we're given, we have a mass of 29 grams, and we have a volume here of 750 milliliters. Now, neither of these match the units we need for concentration. We don't have moles and we don't have liters, but we have knowledge to be able to figure out what the units are in moles and what the units are in liters. The easy one is to change volume into liters. Do you remember how to do that? So milliliters to liters, you divide by 1,000. So when you divide by 1,000, you should get 0.750 liters. Next, if we want to find moles, we have a mass. And lucky for us, we know what the compound is. It's sodium chloride. So here, if we want to find out the moles of sodium chloride, we can do that by using our molar mass of sodium chloride. So if you want an extra little practice going from mass to moles, you can pause the video and try and calculate the moles yourself. And then once we have that, we'll put it together and find molar concentration. So if you've tried this out, you take your 29 grams, and we know we're going to divide by the molar mass, which is 58.44 grams. And we get about 0.496 moles. Now we have our volume, we have our moles, we can calculate concentration. So our moles go on the top because we want moles over liters or moles per liter. 0.750 liters on the bottom. And you should get somewhere around 0.6616 moles per liter. And then again, don't forget to round to significant digits. This is 2 significant digits, and this is 2. So our rounded answer should be about 0.66 moles per liter. So that's one question that you could encounter where you're actually asked to calculate molar concentration. There are other questions involving molar concentration that might get you to try something else. So let's take a look at example number 2 and see what it's asking us for. What mass of sodium hydroxide is needed to make 750 milliliters of a 0.125 mole per liter solution? So if you think you know what to do with this question, or if you want to give it a try, you can pause the video now and try it out. If you're not quite sure, we'll walk through the answer next. So, the question's asking us for mass. here we're told what the compound is, sodium hydroxide. But to find mass, we'll need its chemical formula. So, chemical formula for sodium hydroxide, if you need your list of polyatomic ions in your periodic table to figure that out, that's fine. But this is sodium hydroxide. We're given a volume, 750 milliliters, and we're given a concentration is 0.125 moles per liter. So here we've got a scenario where we want to find mass, but we're going to figure that out using concentration and volume. So remember your molar concentration formula is C is equal to N over V. If I want to find mass, the only thing that connects mass in this formula is moles. So the first thing I'm going to need to do is use my concentration and volume to find my moles. So I'm going to rearrange my formula. I need to bring the volume up from the denominator in the numerator. So that will mean moles is going to be equal to concentration times the volume. Now when I look at my units over here before I actually do the calculation, I've got moles per liter and here is milliliters. So don't forget we need to have liters, so change your milliliters to liters. Once you've done that, you can put in your concentration and your volume and find out how many moles you have. And you should get about 0.09375 moles. Okay, now that we have moles, we can move on and solve for mass. We know the chemical formula of sodium hydroxide, so now what we need to do is find its molar mass and use that to find out how many grams we have. So we're going to take our moles that we just calculated, and we're going to multiply it by the molar mass this time, because we want grams in the end. You can see your units are going to cancel out, and it should give you about 3.75 grams. But again, don't forget about significant digits. When you go back and look at the question, 750 is just 2 significant digits. So here, make sure you round to 2 significant digits. Now, just like some of the other problems that we've seen involving moles up to this point, especially the ones with stoichiometry or multi-step problems, if you wanted to combine these two steps, this step here with moles and this step here with mass into one line to solve, you can definitely do that if you like. If you're curious how this looks, I'll just give you a quick rundown over here. If you're not sure or this is too complicated for you, you don't have to try and put it all in one line. But it's basically the same two steps. Take your concentration, multiply it by the volume, or you could have even put the volume first and the concentration second, it doesn't matter. Liters and liters cancel. And then you multiply it by your next ratio, which is the molar mass, 40 grams per mole. And you can see moles and moles cancel. And then you're left with grams for your unit, so you know you've done the unit analysis properly. And then in your calculator, you would do 0.125 times 0.75 times 40, and it would give you the same thing, approximately 3.8. So if you like those multi-step calculations put into one unit analysis line, you can definitely use that here. If not, you can stick with a two-step problem and you're okay. All right, now let's take a look at another type of calculation for concentration. This one is percent concentration. Where do you see percent concentration being used? This is common in intravenous medication. This is common in over-the-counter medication. toothpaste, vinegar. If you have any of these things at home, you can take a look at the label after you learn this lesson, and you'll see the concentration expressed as a percentage on there. But toothpaste with fluoride and vinegar for the acetic acid, you'll find those percentages on there. So there's three types. They're all set up very similarly. There's one volume percent, volume of your solute over volume of your solution times 100%. Here the units don't matter as long as both of them are the same. So milliliters and milliliters, liters and liters, they just both have to be the same. Then there's some that are involving mass. So this one's called mass volume percent. It works very similarly. Mass of solute over volume of solution times 100%. And then there's one more that you'll see, and it's got two masses. Mass of solute over mass of solution. Again, here the units don't matter. It can be grams and grams or kilograms and kilograms. That's totally fine. Another notation that you might see when coming across mass, mass is more scientifically accurate, but sometimes it's referred to as weight volume. And so instead of an M, they'll use a W/V for percentage, or mass is sometimes called weight. And that would be W/W percent. But we're going to typically see more mass. One thing to remember, on the bottom here in the denominator of all of these formulas, we see solution. Remember, the solution is made up of both the solute and the solvent. So just pay attention to the questions that you're seeing, because sometimes it will give you the volume or mass of a solution, and sometimes it'll give you separate solute and solvent masses or volumes. So just pay attention. So let's try out a problem involving percent concentration. Determine the percent concentration of a solution made by dissolving 140 milliliters of acetic acid in 500 milliliters of water. So here we're trying to find percent concentration, but to figure out which of the three we're looking at, we need to look at the measurements that are given. First, we're taking 140 milliliters of our acid and dissolving it in water. So here the acid is our solute. It's in the smaller quantity. Okay. Next, we've got another volume, but when we look at it, this is just water. This is the volume of our solvent. It's 500 milliliters. If we're finding percent here, since we see our two measurements are in volumes, that means our percentage will be volume percentage. To find percent by volume, remember what we need. We need volume of our solute divided by volume of solution times 100%. Volume of solution goes in the denominator, but this is solute and solvent. So here we have to do this calculation before we go and find the percentage. 140 milliliters of the acid is added to 500 milliliters of water. So the total volume of our solution is 640 milliliters, and that's what we need for our denominator here. So let's go ahead and find that percentage. So we take our 140 milliliters, divide it by 640 milliliters, multiply it by 100, and we're going to get about 21.875%. And just like all of other problems, make sure you round to significant digits. So here we've got 4 significant digits for 140.0, and for 500.0 we've got 4 significant digits, so our final answer needs to have 4 as well, so 21.88%. There are other variations on these types of percent concentration problems. They're not any more challenging, but they get you to solve a different variable in the formula. So in this example, we found percentage. In some of the questions, maybe they'll get you to find the volume of the solution if they give you the percentage, or volume of the solute, and so on. So you'll have a variety of types of problems you can practice. Last one here, type 3 are very low concentrations. So these are ones that are very small. Where do you see these ones? Water testing is a big one. So things like minerals, ions, heavy metals, anything like that, very big in there. Another place, soil testing. A lot of environmental testing, you'll get reports of very low concentrations of different things. So what are our very low measurements? First one, parts per million, ppm. What kind of approximation can we make that you'll understand what this means? So imagine you have a regular sized bathtub, you fill it up with water so it's full, and you put in 1 drop of red food coloring into the bathtub. That would represent pretty close to 1 part per million. Can you see the red food coloring once it mixes in with the bathtub water? Probably not. It just looks like regular old bath water. But you know you've put that 1 drop in there, and you know floating around somewhere the color molecules of that red food coloring have just dispersed and spaced out so much. We get even smaller with ppb, parts per billion. If we want another approximation to give you an idea of how this would work, we'll do the same analogy with the 1 drop of red food coloring, but imagine you have a regular sized swimming pool full with water, and then you put that drop in. Are you going to be able to see that red food coloring? Definitely not once it mixes with the water. But you've put that drop in there, you know those molecules are floating around, it's just very, very, very dilute. 1 more parts per trillion, this is even more tiny. Imagine you had the volume of 1,000 swimming pools and you put 1 drop into that volume of water. That would represent a part per trillion, so very little. Why do we care about representing very low concentrations? Some things are very toxic and harmful even in low amounts. Lead is a big one if you're looking at lead and water testing. Even small amounts of lead are bad. Mercury is another one that's of concern, especially if you eat any kind of seafood or fish because of pollution and contamination. Um, those are things to watch out for. So how do we calculate these different types of measurements? There's 3 formulas. They look very similar to one another, and even somewhat similar to the percent concentration that we just saw, but a little bit different. So they all have a mass of solute over mass of solution. That's consistent for all 3 of them, but their factors vary. Parts per million is 10 to the power of 6. Why is it 10 to the power of 6? Well, 10 to the power of 6 is 1 million. So that's where the parts per million comes in. Parts per billion is 10 to the power of 9. 10 to the power of 9, when we write it out, is a billion. And you get the idea here. 10 to the power of 12, lots of zeros, is a trillion. So that's why we're using those powers of 10 here to help represent the million, billion, and trillion component. The other thing that's not shown here, there's no units. As long as you have your solute and your solution in the same units, then it doesn't matter which units you use. So let's try out a problem. and see how this works. In a chemical analysis, 2.2 milligrams of oxygen was measured in 0.250 kilograms of soil. What's the concentration in parts per million and parts per billion? So let's take a look at what we have. We've got a small amount of oxygen in a big sample of soil. So the oxygen here has to be our solute. This question says it was measured in 0.025 kilograms of soil. So this 0.250 is the total volume of your sample, which would make it the total solution here. The oxygen is already part of this. Then we want to find out parts per million and parts per billion. When we look at these units, they're not in agreement to one another. We've got milligrams and kilograms. So one of them you could change to milligrams. If you wanted to change kilograms to milligrams, then they would both match. Or you could change the milligrams to kilograms, they would match. Or you could put both of them in grams. It doesn't matter, it will work out to give you the same answer, but as long as they're both in the same units, that's what you want to go for. So, if I'm going to go from milligrams to kilograms, or kilograms to milligrams, let's do a quick review of conversions, just for anyone that needs it. So, if I'm going to go from kilograms to grams, I multiply by 1,000. If I go from grams to milligrams, again, the factor there is 1,000 and I multiply. If I'm going from milligrams to grams or grams to kilograms, the factor is still 1,000, but I'm dividing in this case. So it doesn't matter which one we do. Let's say we change kilograms to milligrams. So kilograms to milligrams means I'm going to need to multiply by 1,000 and then multiply by 1,000 again. So if I do that in my calculator, I end up with 25,000 milligrams. Now I've done all the work to be able to find my parts per million and parts per billion concentration. So let's go ahead and do that. If you want to give it a try, you can go ahead and pause your video at this point and plug it in and see what you get. And then when you're ready to check, unpause and we'll continue the question together. So here we need mass of solute over mass of solution times 10 to the power of 6. So I take my 2.2 milligrams divided by 25,000 milligrams multiplied by 10 to the power of 6. And then when I do that in my calculator, I get 8.8. Sorry, I take that back. It's not 8.8, it's 88 parts per million. Always double check your answers. All right, let's try it for parts per billion. Or if you haven't tried one yet, now that you see how parts per million work, pause it and try out parts per billion just to see if you can get the hang of using the formula yourself. So remember, with both of these formulas, they look the same, except for that 10 factor. This will be 10 to the power of 9. So 2.2 milligrams divided by 25,000 milligrams times 10 to the power of 9. And then here we should get a bigger number than parts per million because the difference between the two should be a factor of 1,000. So here you should get 88,000 parts per billion. So those are three different ways of calculating concentration that are very common: molar concentration, percent concentration, and very low concentration.